Well, we're going to do some solutions of differential equations. First order differential equations, dy dx equals f of x. Secondly, second order differential equations where we've got a second derivative, and that's d2y dx squared equals f of x. Okay, and they're easy, guys, so let's just get straight into them. First of all, we'll do part A, where we've got dy dx equals f of x, yes? This is what we have to do. We just take the antiderivative to solve them, to get y, okay, with respect to x. Yes, f of x with respect to x, integral of, don't forget the dx, otherwise that's wrong. That causes tremendous offence amongst the examiners, alright? So don't forget the dx, okay? Alright, let's do them. They look easy. Let's do A today. Hooray, dy dx equals that beast, so we're just going to anti-differentiate with respect to x. Now, that gets you 1/5 of x to the 5th minus, now one more than this exponent here is 3, so that'll be 3 over 3 x cubed, which just gets us minus x cubed, plus 2x plus c, and fills us with glee. Number B, okay, dy dt is sine 2t, okay, well that's easy, isn't it? It's just going to be minus a half of cos 2t plus c. Now, as to whether you're supposed to put where c is any real number, I suppose you really are supposed to, because you should define any variable that you put, or any pronumeral that you put into an equation, but it's pretty well generally understood that that's what you mean, so I don't think you'll get that wrong. In fact, I'm sure you won't get that wrong in the exam, at least in the exams that I am part of the system of here. But, you know, if you're in any other system, any other place in the world, you might have to put where c is an element of R, the real number set. Alright? Do you get that? Okay. Number C, alright, what have we got here? Dx dt equals that. Yeah, that's alright. So that's going to be minus a third of e to the minus 3t plus the log of modulus of t. Remember that modulus, otherwise you really are wrong. Because t can't be negative. T cannot be negative. Well, actually, t can be negative, but the log of anything can't be negative. The anything here in this position, log, can't handle negative numbers, right? So you have to put a modulus around here to protect the log from getting a negative term here to take the log of, right? And here's your constant of integration. You must put that in. You must put that in because they're asking you for the general solution. General solution means you must include the constant of integration. Okay, otherwise the answer is actually wrong. Okay, Mr. Box, hello to you. Thank you. Now, D. Here's D. This is the confusing one I was talking about before. Let's integrate with respect to y, and that gets us a inverse tan y thingy, doesn't it? Right? X to inverse tan y plus c the constant of integration. Now, if you were asked for the solution in terms of y, which you aren't in this case, you would then take c over to the other side as x minus c equals inverse tan y. Then you would take the tan of both sides. So you get tan of x minus c equals tan of the inverse tan of y, which just gets us y, because tan of the inverse tan kind of like they neutralize each other and just get you y. Okay, there. Now, that's what you would do if you were asked to solve y, but otherwise you wouldn't bother with that, because if you did do that and got it wrong, in the exam system of which I'm a part, they would take marks off you even if you weren't asked for it. But if you played with the answer and got it wrong, you would have marks deducted, which is also very nasty. Okay, you happy? Good show. Let's keep going then, if you're happy. We've got to find the family of curves e.g. aka general solution, that's all that means, whose gradient is e to the minus 2x, and we have to find this is here is a specific solution which passes through this point on the original curve of, we'll call it y, shall we? Let's call it y. Alright, so part A, there, I'm calling dy dx e to the 2x, and therefore I'm going to anti-diff that, and I'm going to get y is a half of e to the 2x plus c. Okay? That's the general solution. Don't leave the c out. Don't leave the c out, otherwise you're wrong. Yes, it can have any real number value. B. Now, this is a specific solution which we're going to substitute our value of x as 0 here and y is 3 into it to work out what c is in this particular instance. Sub naught and 3 in, what do you get? 3 equals half of e to the naught, okay, plus c. E to the naught is 1, so that looks like 3 is a half, plus c must be 2.5, guys. Must be. There it is. So therefore our specific solution in this instance is y is a half of e to the 2x plus 5 over 2. Woo-hoo. Okay, here we go. Now this is part B. This is differential equations, second order differential equations, where we have to take the antiderivative twice to sort the beasties out, which is a bit annoying, but hey, we can do it. Okay, we've got this line up. Okay, we're going to demolish them, guys. We're going to own them. Let's go for it, okay? A. Now we've got d2y dx squared is that. Now, okay, let's go for it. We've got to anti-diff the first time to get dy dx. Okay, so it's 10 over 4, x to the 4, minus 3 over 2, x to the 2, plus 4x plus c. Yeah, okay, that's alright, no problem. Better simplify this beastie. Okay, now we'll anti-diff again, okay? So, be careful, it's getting a little bit complicated. Y is going to be, that's 5 over, that's where that comes from, up there, 5 over 2 times 1/5 of x to the 5. This 3 over 2 was already there with a minus in front of it. Now that'll be 1/3 x cubed, and that 4 was already there, and that gets us a half of x squared plus cx. Now look at this, plus another constant of integration, which we're going to call d. Okay, you don't want to use c because that's really saying that the constants of integration are the same, and that's by no means true. Okay, it could be completely different constants of integration. The only thing that we need to say maybe about c and d is that they could be a member of the real number set. They could be any real numbers, all right? Any members of the real number set. Now, I think we better clean all that up. It's a bit of a mess, isn't it? Like the dirty washing. We better clean it up. So those 5s will cancel, won't they? Looks like these 3s are going to cancel, and I think 2 goes into 4. Well, in fact, I'm sure it does. And then that leaves us with, be careful now, 1/2 of x to the 5 minus a half of x cubed plus 2x squared plus cx plus d. Now I've put it in there for correctness, where c and d are real numbers, elements of the real number set. Okay. Now, if you're in an exam system, at least the one that I'm part of here in Australia, you won't be penalised if you don't put that in. But it's mathematically strictly incorrect if you don't. You know what I mean? Because you've got to define any pronumerals you start introducing into equations to make complete sense. Alright? Part B, here we go. d2y dx squared is cos of 3x. Well, that's easy. Therefore, dy dx would be 1/3 of sine 3x plus c, and y would be, now think of it, minus 1/9. You have to put the minus because cos gives minus sine as a derivative, therefore minus cos gives plus sine as a derivative. Okay, minus 1/9 cos of 3x plus cx plus d, where c and d could be any real numbers. Put a box around that, and Bob's your uncle. Alright, let's do number C now. d2y dx squared is e to the minus x. That's really easy. So therefore y would be minus e to the minus x plus c, and then go again. Therefore y would be plus e to the minus x plus cx plus d, where c and d are any real numbers. Alright? Good. Now this one coming up is the hardest one on the page, but it's not very hard anyway. d2y dx squared is 1 over root x plus 1. Now this is a linear substitution one. I wonder whether you spotted that. So we're going to make u equal to x plus 1, and therefore du dx equals 1, and therefore du equals dx, and now we're going to say that dy dx is the integral of that thing, which it is, and now we're going to substitute for u. There it is, right? It's just very simple, isn't it? U to the minus 1/2 du. Now, what's more than minus 1/2, ladies and gentlemen? It's plus 1/2, so it'll be 1 over plus 1/2 u to the plus 1/2 plus c, which comes out to be 1 over 1/2, of course, is 2. Now we're going to substitute for what u was, which was just x plus 1, and there's your answer. Okay, there's your answer, but of course that's only dy dx. Now, having armed with the knowledge of what we did up here with this variable substitution, we can do the same thing here. Okay, we would know therefore that the antidiff of this would be 2 times, now 1 more than 1/2 is 3 over 2, so it's 2 over 3 over 2 times x plus 1 to the 3 over 2 plus cx plus d. Are you right? You get that? Yeah, and this thing here, be careful, this comes out to be 4 over 3. So the RSUB, 4 over 3, x plus 1 to the 3 over 2 plus cx plus d, where c and d are any real numbers. Okay, happy with that? I know you are. Very good. Excellent. Now, what do we got here? Given the differential equation d2y dx squared equals cos squared x, find the general solution in A, and then the solution given that dy dx equals 0 when x is 0, and also when x is 0, y is minus 1/8. That's all right. Look, that's a piece of cake, guys. If you know how to anti-diff this, it's a piece of cake. And I showed you how to do that in a previous video on anti-differentiation of trig identities, or trig functions, I mean. So A, the general solution, it's going to be, look, this is dy dx will be the integral of this with respect to x. It's an even powered exponent, therefore we use double angle formula, don't we? We do. There it is, look, in all its glory. So now, well, let's just anti-diff this thing. We'll just get x plus a half of sine 2x plus c, and for goodness sake multiply the bracket out because we have to go again in a minute and anti-diff again. So don't make it too confusing for yourself. That looks good to me. Now that's really easy to anti-diff that, isn't it? Yeah, so let's do that. That's x squared over 4 minus 1/8 of cos 2x plus cx plus d, where c and d are any real numbers. I think that deserves a box. Hello, Mr. Box. Hello again. Right, now, are we happy? Oh yes, now we've got to do this specific one, don't we? This specific one. Alright, come on, we'll do that. B. Now we'll go back to the dy dx expression, there like that, and now we'll substitute, what are we going to do? Substitute dy dx is 0 when x is 0. Alright, so we get 0 equals 0 plus sine of 0, which is 0 anyway. Oh look, c is a non-event, c is 0. There you go. C is 0, okay, so we don't have to worry about him. So let's just restate the derivative function here. It's that plus that, right, without any c term. Now we've anti-diffed again. Now I'm anti-diffing in light of the fact that c is 0. So it becomes x squared over 4 minus 1/8 of cos 2x plus d. Now we're going to sub in our boundary conditions here. Y is minus 1/8, x is 0. So we get minus 1/8 equals 0. Minus 1/8 cos of 0. Now cos of 0 is 1, so that means, oh, minus 1/8 equals minus 1/8 plus d. I think d is going to be 0 as well. My goodness, how cunning. It is, look at that. So therefore our solution, our real specific solution, specific to this instance where we had these initial conditions, is this beastie. Okay, you happy with that? I am. I'm delighted. Okay, so let's go. Oh yes, the last little bit for you. The last little bit for you, this is the end, is the trig thing. Let's go back to where we were. We got to this. Now if you were in a CAS active exam, guys, you could easily do this without all the palaver and all this, but this is important to know how to do it. But if you just were in a technology active exam and you just wanted to get the solution to this, here it comes over the page. Dsolve. Dsolve is in your menu of your CAS device if you've got a TI device like we do at my school. Now watch this syntax. That's y dash dashed equals cos x all squared, and y when x is 0, y bracket 0 equals minus 1/8, and y dashed 0 equals 0, comma, then that's the independent variable, comma, then the dependent variable, okay, and then close bracket and hit enter, and you'll get this delightful expression over here, which, if it's not to your liking, I'm about to show you this marvellous little cleanup thing called T-collect. It stands for trig. T stands for trig collect, but you can put this, you can just recall this previous answer here, down into this entry line here, or, you know, copy and paste it or whatever, hit the entry line, and you'll get something, generally speaking, which will be cleaned up and tidied up and made to look a little bit nicer, packaged a bit nicer, and with less sort of ragged loose ends around it, you know. So remember T-collect, it can actually save your life in some exam settings, particularly if you're doing trigonometric solves. You can get some pretty beastly looking expressions, and T-collect sort of like, you know, just cleans it all up and makes it kind of bearable and nice and neat and, you know, giving you a good feeling as if you've got the right answer after all. Alright, I think that's the end. I think that is the end. And yes, the end's your friend. And go forth and do plenty and get good at them. And thank you for coming to see me today. And you have a wonderful day, and we'll see you next time.